Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're really happy to have Songyup Han here. He is a PhD candidate at the University of Washington. Songyup does distributed systems, networks, and security. He's also just an example of a very complete systems builder, is how I would put it, able to do great analysis and fantastic systems building at the same time. He's built a variety of systems, and not only has he published in our top systems and networking conferences, but he's also published at places like Chi and NIPS and WWW. So we're really looking forward to his one-on-ones with everyone in the lab. Thanks, Songyup.
Thank you, Sid. So hello, everyone. Can you hear me well in the back? Great. So thank you for coming to my talk. So today I'm going to talk a little bit about my research and some of the future directions. As mentioned, I have pretty broad interest in any areas in computer science. Worked on the distributed systems, security, privacy, Ubicom, and some machine learning and computer vision related stuff. So before starting my PhD, was studying in South Korea and worked as a software engineer for 3.5 years, and then started PhD in 2010. So I also did internship in MSR 3 times before, twice in Redmond and once in Cambridge, although this is actually first time being in New York City. So thank you for having me here. So today's talk, among many different research projects, I will be a little bit focusing on the systems and security stuff. So let me start. So in recent years, how people use computing devices has evolved rapidly. So we have many different devices, like from traditional computers, laptops, to smartphone, tablets, and or like smart watches and glasses. And now the Internet of Things suggests all devices around or around us will have some sort of computing power and connected to the Internet. So along with these new devices, we have many different applications which access our personal information. So the amount and the type of personal information have ever been increasing. It includes users' location or contact address, health information, or some of the application may use your search queries. So it becomes very easy for users to access those information through the new devices. Unfortunately, not only the users, but the other parties can easily access users' personal information as well. And when we are using Internet, there are many different entities which we can't trust or we can rely on. So these are raising the security and privacy risks. At the same time, users may not understand how their information is exposed, and also they do not have much control about the information exposure. By the way, feel free to ask any question during the talk. So apparently we can't change the first two points. So I'm trying to address the third point. So we want to give users control over how their information is exposed and used from the remote services. What does it mean? So let's look into the simple diagram showing the entities involved in the Internet communication. So you may run some application on your computer, your smartphones, and it's connected to the Internet, and they are talking to the remote services. So throughout my PhD research, I have studied various issues in each environment. So first, for the application, I worked quite a bit on the smartphone privacy and risks. So back in 2010, it's kind of the Android system becoming very popular. So one of the great things for the smartphones, not only Android, but iPhone or Windows Phone, it's great to download any application from the application market. While we could enjoy the functionality from the third-party applications, it was pretty unknown about how the application used our personal information, whether they are just used in the phone or send the data. So I participated in the Android project, which is information flow tracking system, that reveals where does the information, your location or any other information goes to which server. So they can say, oh, your location is being sent to like Bing map. It's fine, but it's also being sent to the advertising server. Based on this project, I was also proposing a privacy protection mechanism to say, selectively give application some real or fake information, or block unwanted information leakages. Also worked on studying for third-party tracking, like advertising or analytics in the smartphone context, and also security vulnerabilities in smartphone by combining static and dynamic analysis. So moving on to the next target. The network can be untrusted or unreliable. Fundamentally, the current internet architecture was not designed with the security or privacy considerations. So I was looking into how we could redesign the whole internet with the principle that all the network elements use very minimal information for the communication. So, and finally, there could be a little more obvious adversaries at the remote servers, well, adversaries to the users, which I will talk a little more in detail today. So in this talk, I will talk about how we should design systems when the remote servers are not reliable or not trusted with two example systems. The first one is called MetaSync, which is a file synchronization system across multiple untrusted storage providers, like a Dropbox or OneDrive in Microsoft. And then I will talk about something called the pseudonym abstraction, where each application or user can use many pseudonymous identities to control over their information exposure. And then I'll briefly introduce some other work I did and future directions. So let's talk about the MetaSync first. So there are many different cloud services now. Among them, I was looking into the file sync service. So one of the most popular service for the user end, and also many applications rely on the file synchronization services. So the service like Dropbox make it easy for the users to to store their files in the cloud and access from many different devices. Also to prevent what's happening? Interesting. Okay. Oh yeah, my purse is gone. And also we are using those services for sharing files with other friends, collaborators. So with this convenience, they are getting much popular. So last year, the Dropbox announced that the number of their users reached 400 million. And there are also similar services provided by many different companies, including Microsoft. And recently, some of the Chinese companies started to provide like 2 terabytes of free space. So this sounds great, but the question is, however, can we rely on a single service for storing whole our files or for sharing files with other friends? While we, the users, may expect those services to work well, fundamentally, there's no reason to trust those service providers. So some of the services may come from like smaller companies, so they may become unavailable time to time, and some others may be provided by the companies which located in some other country, which we may not really trust. So in fact, there have been many incidents that, you may have heard of news that your data stored in those sync services at risk, even with relatively trusted companies like Dropbox or Apple. So we could think about building a totally new system from scratch to use those cloud services with minimal trust. And we've seen quite a bit of systems from the distributed systems research. But here, in this project, I want to tackle this problem from a little bit different direction. So we are building a file sync system by exploiting multiple existing services. So while each service has its own unique feature to differentiate from others, their core functionality is to allow the users put their files into clouds and access them. So each service has third-party APIs for other applications to build on top of their APIs. So we are going to build a system upon those APIs. And by combining them, I can have better service. Better service means higher availability, greater capacity, higher performance, and stronger confidentiality and integrity. So, and in addition to those goals, we had 2 more goals in MetaSync. So we don't expect communication between those service providers because they are served by different companies, and we are not relying on communication among clients as well. And we are not going to introduce new servers from our point of view. So every implementation is done and run in client. So from the goals I just mentioned, there are 3 key challenges in the system. So first, we need to maintain a globally consistent view of the synchronized file across multiple clients. I will be explaining a little bit more about this. And we are using only the service providers' unmodified APIs. We are not going to tell them, hey, you should modify your APIs for us. And finally, this system should work even with the presence of some of the failing services. Let's how we design this. So this is the overview of the design. There are 3 subcomponents. So first, the object store for maintaining files, and there's a synchronization and replication subcomponent. And it's connecting to the backend APIs, backend service through their APIs. And we define common abstraction for the services so that we can easily plug in the new service whenever we need. And finally, MetaSync also interacts with local file system. And there's a layer between here which does encryption and integrity check when they are sending the files to the backend or downloading files from the backend. And the first thing, the object store holds files, copies of files, and those copies will later be replicated and synchronized to the backend services. And this has a similar architecture with any other version control systems like a Git or SVN. So they are using, this system is using content-based addressing and hash tree. So by using content-based addressing, we are naming the files with its hash of the content. So it can automatically deduplicate if there is some same contents in the different files. And all those very simple integrity check. So we can check whether the name is matching with the hash of the content when we are downloading the file. And finally, because file name is unique, it can modify or download independently to each other client.
So I just have a high-level question about the system. Is this something you're proposing that an end user do with a bunch of cloud services? And if it's not, what's the difference between just having a cloud service implement, all this system stuff to make their file storage more reliable versus having the user use a bunch of services with this thing in front of it, to make everything more consistent?
Right. So the end user, it's kind of close to the former point. So it's kind of end user is running the system, and we are spreading the files into the multiple different backend services. So sure, each service provider can have better or more reliable service from their point of view, but from the users, we are kind of spread our trust over multiple providers. And it's mentioned directories form a hash tree. So what it means is the inside of the object store would look like this. So directory maintains pointers to a file, and files are chunked if file size is too big, or files in a directory can be merged in a single object if file sizes are too small. And from this hash tree, the hash of the root is uniquely identifying the current snapshot. And when some of the files modified, like here the large.bin is modified, what happens is the object store will create new blob for the modified version and updates its parent pointer recursively. Finally, there will be new hash value, which is defining the updated snapshot. And then, as mentioned, the blobs here, it's kind of describing how, I mean, this tree is describing some logical view of the object store system. And we are synchronizing the blobs into the backend service, as mentioned. And simply saying, we are,
So a file is made up of multiple blobs,
Yep.
or a blob contains many files?
So it can happen both. I mean, what it means, we have defining some threshold. So if file size is too small, then we can put the multiple files into a single blob.
Okay.
Or if file size is too big, we can chunk down into the multiple blobs. Yep.
How much client-side storage are you using?
So this is kind of replicating the whole file system, I mean, the directory dedicated for being used in the MetaSync system. So it's kind of doubling the space.
So if you have n bytes, you're going to have 2n client-side storage.
And plus little overhead for metadata. And also we can keep also the previous version as well if the user wants. So in that case, it can grow more. But
do you see a way to avoid the factor of 2?
so it's a possible, like, because we can build the object on the fly when it requires to, for example, synchronize to the backend or downloading from the backend. So it's possible. So it's kind of trade-off between like computation and the storage. And usually what we have target as like several hundreds gigabytes of synchronization or several like, it kind of depends on the application or usage model. For example, sometimes in the mobile device, you may want to download only some subset of the files. So there are several different ways to approach that, but it's kind of very naive first implementation of the design. So we are replicating the object redundantly across the R storage provider. The R is configurable number. So if the R is 2, for example, the blob can be replicated like this. I will not go over detail for this. The main idea is we are using some sort of deterministic mapping function. So when a blob is given, we can calculate hash, and we are giving that hash into the function. And the function will say, hey, this blob should be stored in the OneDrive and the Dropbox, or the other blob should be stored in the Google and Dropbox, or etc.
Are those encrypted?
So encryption as we have option to encrypt. So it can be encrypted before storing. And then the functions are kind of, can I say, it doesn't matter where it's calculated for this specific function.
I guess maybe my question is, are you worried about Dropbox failing and losing your data, or are you worried about Dropbox being hacked and someone looking at what you have stored on Dropbox?
Yeah, I think that we are trying to, address both of the issues. So if
you store it in plain text.
Yeah, I mean, we are there again. There's an encryption layer, so the users can say it want to be encrypted, then it's encrypting before sending. So yeah, I will talk a little bit more about the synchronization itself, because as mentioned, each blob can be independently uploaded or downloaded, because they are different if the names are different. But if there are two clients or more clients, and they are kind of each of them is modifying the files, and what happens is if they are claiming or concurrently trying to update what's the most recent version, it'll be a problem. Although the other many services are also looking into the same problem. So let's look into what's happening. So at the beginning, everything's, let's assume there are 2 clients, and they are synchronized to the same point. And if the client 1 is modifying files, only the client 1 is modifying files, then it can update the global view by saying next version is whatever it has, and the other clients can catch up. But if both clients modify files and they are trying to, concurrently say, hey, next version of V1 is my head, not the others, then we need some way to determine which of them should be selected for the next version. And then the other clients can catch up, by merging onto that master. So this problem, determining orders in distributed systems, is a traditional consensus problem. For example, we can use a Paxos or a 2-phase commit for making agreements. For example, the Paxos is a multi-round, non-blocking consensus algorithm, and it's known to be safe regardless of failure, and it can progress as long as majority is alive. But the problem here, we don't have those APIs. We don't have Paxos APIs. We don't have two-phase commit APIs. And also, we don't have communication channels between the servers or client. So the challenge here is we need to handle those concurrent updates and potentially unavailable services, only relying on the existing APIs. So how can we deal with this? So instead of building our own server dealing the Paxos, we are trying to find a way to simulate Paxos given the APIs provided by the current services. Even though there is no Paxos APIs, we could devise a way to simulate with it something called append-only list abstraction. Here, the clients send the normal Paxos messages to the servers. And when the message arrives, logically, when the message arrives, service append those messages into a list. And clients later then can fetch the list of ordered messages to figure out which proposal is accepted. So this abstraction can be built in various ways for each service using their APIs. So we built the append-only list with the comments on a file in Google Drive, OneDrive, and Box. And in Dropbox, we use revision lists. And if those APIs are not available, we could also build this with files in a directory we used for the Baidu.
So you wanted to use Paxos to determine the order of updates that
Right.
the clients are doing.
Right.
And you're implementing Paxos by appending to a list, but the list already implies an order. So why do you need to actually simulate Paxos?
Because some of the service can be unavailable. So if we are we have a single machine. That's actually a good point. If we have a single machine which we know that it's always available, we can just throw that into the service and it will order the message and we can figure out which one is correct. But if some of the services are failing or even some of the services are doing some misbehaving, we need a way like Paxos. It's a kind of same for even if we are building from scratch.
So like you're writing to a list on each one of the services?
Mm-hmm. Yep, I will explain a little further, yeah. So this is what we called as a passive Paxos, because backend service work as just passive acceptor. And they just log messages, and clients can fetch the messages. And the client, the acceptor's decision are made in client as if it would have done in the acceptors. So in this diagram, each client can propose a new route, for example. Say the gray one saying the new route is 1, and green one is trying to say the new route is 2. And after fetching those list of logs, it can claim that, okay, or it can realize that accepted route as 1. So this is a simplified diagram, an actual algorithm. This is done through a multi-round as prepare promise and propose accept as in the actual Paxos algorithm.
So can you
Yeah. Although, again, it needs to be done through like prepare stage. It needs to be winning there, and then it needs to be actual winning at the proposal and propose stage as well.
All right, so I'm sorry, but like, so Paxos cannot make progress if, you know, if not all the services are live, right? Like, that's FLP.
Yeah.
Now, so what you're waiting on here on, like, to make progress to you know, for liveness,
Right.
to get the termination property, is that eventually you'll be able to actually retrieve these logs from the different servers.
Mm-hmm.
But if you could retrieve these logs from the different servers, then you can just say, I'm just going to read the head of that log, and then that's it.
Sorry?
And then that's it, like skip Paxos. If I'm waiting anyway to retrieve the logs from these different servers, then I'll just read the head of that log rather than just going through all of them and simulating multiple rounds and whatever.
I think you can tolerate a minority of failures, right?
Yeah.
Paxos style.
Right.
So he can tolerate a minority of unavailable.
So it shares the same property with the Paxos, because we are actually simulating Paxos. So yeah, we can talk a little more detail
Okay,
further.
awesome.
So we implemented this MetaSync, the prototype of the MetaSync in Python, because all the services are providing their APIs in Python. It was about like 8,000 lines of code. We are supporting 5 different backend services, and we have two front-end clients. One is similar to the version control system, which is command line, and the other is a synchronizing daemon. So you can dedicate a folder to be periodically synchronized to the backend. For the evaluation, we check the kind of end-to-end performance. We have another numbers in the paper, but for this, we synchronize a folder between 2 computers with using the clients from the services and the MetaSync. I presented 2 different workloads here. The one is Linux kernel source code, which has many small files and directories, and the other is like about 50 photos. And you can see the MetaSync is outperforming quite a bit for the synchronizing small files, because we mostly merging the small files into a single blob. And then the many services have very poor performance, throughput when downloading or uploading the small files. And then also we are using the para upload or para download. So performance is not really something very important top kind of evaluation criteria, but it's kind of good to have to see, okay, we have some performance service on top of the APIs.
So I guess what happens if my computer breaks down? Okay, so I guess like you still kind of require me to be kind of then storing my client information somewhere else. So I guess, right? So since you're storing everything as blobs, it looks like you need the set of you need the meta information sit on the client side so that you can access all those blobs.
Right.
And then just put it together
Right.
correctly. So do you have is there maybe there's a standard solution on how to deal with that? I'm just kind of wondering, like, you know, if client is really just my computer and it breaks down, then all these blobs are completely useless to me.
So could you explain a little more? What do you mean by break? Like you can't access.
I spill coffee
So
on my laptop.
right. So the thing
Meta
is,
information.
yeah, the meta information is stored in the backend as well. Right? So as long as you can access the backend service, you can rebuild that. So meta information is not only stored in local.
I see, cool.
Right. Yeah. Just wondering what's the level of the disruption there, but
It makes sense that you get a lot of performance boost from
yeah.
aggregating files into blobs. So I'm wondering, actually, do you have a measure of how much slower or faster MetaSync is versus sending all the blobs to one service?
Right, so we don't have measurement. As mentioned, that's kind of probably really not fair comparison to the native clients. Also, they are not really optimizing to the performance. They kind of want to just correctly storing the files. But yeah, and we don't have the measurement for that. So in summary, the MetaSync is kind of reliable and performant file sync service on top of those popular cloud services. And to achieve the consistent update, we devised a new client-based Paxos algorithm.
I'm just curious, do you envision some other applications for those
Yeah, that's a good question. I was trying to think, but haven't found much yet. So one thing for this, we after devising this algorithm, was looking into several literature and found that actually Lamport was working on that similar problem context. They have something called disk Paxos. And we have comparison in terms of we have little. It can be considered as an optimization of the disk Paxos, and so there might be, but I haven't found some other application for the specific one.
So maybe I missed that, but how robust is it? If everything fails except one service, can you recover, or you need at least two?
So there are two different things. So one is how do we replicate? So in terms of the blobs, and how do we progress in synchronization? Which one is the most recent one? So in terms of replication, it depends on the replication factor. We are saying that if R is 2, it can hold up to just failure of one service, or R is 3 and 2 service. But for the Paxos algorithm, majority need to be alive.
For your simulation, what replication did you use?
So we were using the R.
Or it wasn't a simulation.
Yeah, it's using the R equal to.
R equals 2. Okay.
Yeah.
So that means. What does that mean?
So it means for the file blob, it can be okay with only failure of one service. And I kind of skipping that, but we also have a stable deterministic mapping algorithm. So if you're interested, please visit our website. There's a source code and a paper link. So I've talked about the file sync service with the unreliable or untrusted backend. And it also can prevent remote service from leaking or corrupting files. And next, I will discuss how we can prevent service from linking onto the user's activity. So this talk is about internet tracking. So as mentioned in the very first slides of this talk, there are many different types of personal information. And sometimes it is not really obvious to see the privacy risk. One example is tracking user behavior. So when we are using today's internet, we should assume that most of our activity on websites will be tracked by remote service. You may have experienced that after looking into some of the clothings or shoes, then the advertisement just popped up directly targeting that specific product. So it's one example of the behavioral targeting, and it's done by tracking. So there's some previous work done by Rosnell et al. Saying like among the top 500 websites, 91% embed NS1 tracker, and 88% have some sort of third-party trackers like analytics or advertising. And the web services are well incentivized to build a big user profile because their revenue model is strongly tied to the user how they are understanding the user's behavior. And information collected from the tracking may include from the user's age, gender, or where the user lives to somewhat more sensitive information like political opinion, medical information, or sexual orientation. So let's look into the tracking a little bit more deeply. So in this example, there are two people. Alice is sending a set of queries like Microsoft or route to her home address, and Bob is sending another set of queries. And the tracker may know the first set of queries is coming from some person, and the other set of queries coming from some other person. So what does it mean to us? So information collected the tracker can create a very detailed picture of you. Because of this, we usually think or consider the tracking as something bad, something harmful to us. However, on the other hand, we are getting some benefit as well. Like tracking can be considered as a tool for creating relationship between users and the services. So it can enable personalization, like a recommendation service, or it can be used for better user security, like in bankings. And in some sense, the users, we are also paying for the service by being tracked. So in terms of tracking, the threat model is not just tracking, but I do say the threat model here is that the remote services are tracking users through information in packets to correlate even unwanted traffic together. So what could be a better scenario? So we would like to have tracking look like this picture. So Alice may keep her address from being correlated to her other queries. And similarly, Bob may want to separate his queries related to depression to the others. So even those two sets of queries are coming from one endhost, trackers cannot know whether they are coming from one host or two different endhosts. So we are not arguing, I'm not arguing that we need to get rid of the whole ability for the trackers to link activities from the server side. Instead, we want to provide users with more control over what can be tracked or which activities can be linked together. So by giving users control over what to be tracked, we could alleviate or even remove the problem of privacy risk. And at the same time, we believe that we can still maintain the positive side of tracking. Before jumping into our approach, I will describe a little bit about how tracking works. So the basic idea is service track users by linking their request. And multiple requests from a host can be linked when there's something shared identifier. So many websites are using cookies in the HTTP header to find out where the request is coming from. And even IP addresses by itself are still effective mean for the trackers to figure out, especially when combined with other fingerprinting information. So users, I'm claiming that users should have control with an abstraction covering not only just a single identifier, but all different identifying features, which we call as a pseudonym. And each host manages a large number of unlinkable pseudonyms, and the users or applications can choose which one to be used in which scenario, which context. For example, there could be an ephemeral pseudonym to be used in one-time purchase. And from the previous example, like Alice can be using one pseudonym for medical information and the other pseudonym for her location-related queries. And sure.
I'm curious, so in this view, so if you say you enable users to create these pseudonyms, and say there is a way to create a new pseudonym, cheaply, then like, why wouldn't the user create a new pseudonym in every session? Assuming it can be easily instrumented, and that would just, remove all the benefits from having these cookies in the first place. So it's like, all the privacy and, on the left side and none of the utility on the right side.
So the question is?
You were saying there should be a way to enable some privacy while preserving the utility on the other side?
Yeah.
It seems that from a user point of view, they would rather get all the privacy and just make every session anonymous.
Yeah, but the thing is, it depends on. So how much user wants. If the user just want a privacy, it makes sense. They just want to get more, like every request have different pseudonym, for example, or some way to just protect. But as I mentioned, it's a little bit it could be a little bit controversial whether there's really a benefit by being tracked. But there may, it's a kind of, for the service providers, they are getting good benefit in terms of how they are understanding the user, right? So if we are just removing that factor, it could be disruptive for the service provider side. So I want to kind of maintain the relation well between the users and services. So as an overview, let's see how we want to use pseudonyms. So when Alice is using the one, like for medical information, she has one pseudonym. And if she needs another pseudonym, it's determined by the policy engine from the application side. And if, excuse me, it needs more pseudonym, it can allocate that through talking to the operating system by, for example, allocating more IP addresses. And the operating system, in turn, need to get support from the network, like a DHCP, to get the new IP address, and like routers to the route packet to the correct destination. And then it can get the new pseudonym to work with, like sending another queries to the tracker. So we are designing in a cross-layer manner. So we'll talk a little bit about how we are using that in the application layer, and move on to how we are supporting from the network layer.
Just a question, perhaps there's a straightforward technical reason why it doesn't work, but what would stop you from using browser fingerprinting to connect the pseudonymous identities together?
Right. So that's a good question. So we are trying to say the pseudonymous abstraction should also cover some of the fingerprinting information, although this is kind of illustrating only the cookies and IPs. So for example, there are several different fingerprinting methods, like using the font in the operating systems or using the window size. So ultimately, like in the web browser should control that information as well. For example, they're just giving the same information, same font with like average other people. So there could be different mechanism to build APIs for the several different types of fingerprinting information. But currently, we are kind of illustrating with some notable examples. So from the application side, application need to assign different pseudonym into different activities. So let's assume that there are many, many different pseudonyms available from the computer side. However, how to use it is depending on users and applications. Sometimes people might want to have every packet be a different pseudonym, or they might change the pseudonym for a different account. There are many variations. So how do we know which pseudonym to be used? As a system designer, we actually don't know. So what we do is we are trying to build a flexible way for each application to define their own policies. For example, in a web browsing, policy can be defined as a function of the request information and the state of the browser, like unique IDs for each window, tab, or requests, and so on. So let's look into what kinds of policy could be possible, although this is very, very simple policies currently displayed. So by default, every request has the same pseudonym. So Facebook and, excuse me. And here in this example, Facebook can know that this user is reading some specific article in the news website because it has like button, and then it's matching with the user's previous login to the Facebook. And some extreme case, every request, again, have different pseudonym. But there could be many other like policies in the middle. Like, for example, web browser can change pseudonym according to the page's domain name, the user connected. It means that when a user visits news.com, every image or script use the same pseudonym, and it has a different pseudonym when the user is using facebook.com. So in this case, Facebook cannot know the user's visit to news.com. So I just briefly explained how policies can limit servers' tracking ability.
But
yep.
That also means you couldn't use the like button.
So we can still, but once you use it, then it's kind of giving that information to the Facebook server. So there is another. So it's kind of building some privacy protection mechanism in our policy engine. So there are several different proposals, for example, separating per first party or disable the social button until it's clicked. Those can be implemented.
So after it's clicked, then they know. But if
Yeah.
if you don't click,
Right.
they won't know.
Right.
Okay.
So again, this is not something from us. It's kind of we are kind of demonstrating we could build several other proposals in our system. So let's look into network layers because I'm running out of time. I'll kind of briefly try to brief an explanation. So to support pseudonym abstraction, we need to consider following 3 points NS. So first thing is we need to have, each host needs to have many IP addresses because we want to assign one IP address per pseudonym. And the other is those addresses should be properly mixed. What it means, if they, the IP addresses in a single host are clustered together, the trackers can easily figure out, okay, those clusters coming from the single host. Or on the other hand, if the addresses are just all random, then there's an issue with the router. The routing table could be just exploding because they need to kind of maintain all different entries to route the packet. So how can we do this? So we don't have currently many IP addresses in IPv4, but we are moving toward IPv6 world. So in IPv6, even a small network can get the /64 IP address, which is already much larger than whole IPv4 space. So with IPv6, we will have an environment where each host can have many addresses. And then if we are looking into IP address, what we can realize is the first part is used to route the packet into the network in like a BGP routing. And the second part is being used for routing the packet inside of the network. So once the packet is coming into the network can use the second part as they want. Whatever they want, they can encode information into the second part. So what we did is we are dividing the second part into 3 parts. It's a subnet ID and host ID and pseudonym ID. And the first 2 are actually pretty same with the current internet architecture. And what we do is we are using symmetric encryption to encrypt that 3 together into the encrypted ID. So after encryption, it will look like randomly chosen from the whole IP pool. However, because it can be decrypted, after decryption, it can figure out, the routers can easily figure out which is the next hop for this packet, the destination. So, and those knows only the encrypted IP addresses, and routers use those unencrypted parts by decrypting the packet when it comes to forward the packets. And it uses longest prefix matching with the same information with the current internet architecture. So the efficiency and the routing table size will remain as the same. So I will show us example like how it can figure out. And when packet is arriving, when packet is coming from the destination, it can deliver the packet into the network by looking the prefix with the BGP protocol. And when it arrives into the router knows the key, and it decrypts the packet to see the base address, the decrypted address, and it can figure out what's the next stop, and it does the same thing until the packet arrives the end host. And something to note here is we are decrypting the packet only for the 64 bits, which doesn't incur too much overhead, and it also can be easily delegated into the hardware. So we implemented the prototype as well, because we don't have the IPv6 and control. We have IPv6 usually in the campus network, but we don't have whole control over that. However, there's a IPv6 broker we could use for building the prototype. So for the policy engine part, we were building in the Chrome, the browser extension to have JavaScript function to figure out which pseudonym to use. And we were using the IPv6 tunnel broker, which is connected to our gateway server So there is a tunnel between them, and IP addresses can be assigned in the gateway. So finally, it's being used as a web proxy. So what had happened is the extension as tagging the request was which pseudonym to be used. And the proxy can assign the outgoing socket to have the specific IP address, which is connected through the tunnel broker to the whole IPv6 internet. So for the evaluation, we were looking at two different things. First, we are trying to figure out whether it's expressive enough to implement the various policies. So we were looking into different papers and what kind of protection mechanism was proposed, especially for the cookie side. And we are implementing it in a cross-layer manner. And we could implement many different policies. Many of them are just straightforward, and some of them are very simple, like every request use the same pseudonym, or every request use different pseudonym. We could use a request ID for that. And there's some other things using a little more information to build. And then we are moving toward like whether they are effective in preserving policies. Again, it's kind of testing the policy engine to see whether we could have many different policies. And what we checked is we were kind of collecting the choices from 8 users for 3 days, and every request has some information together with like a request ID and the tab ID and window ID, and we are simulating the policies to see how many activities are exposed to the third party. So there could be many different ways to figure out like whether it's exposed to the first party or third party, and this specific evaluation is to see how many activities are exposed to the third party remote services. And as you can see from the red line, we could reduce quite amount of activities observed by third party while having not too many pseudonyms in the system. So introduced a new abstraction called pseudonym. I will kind of skipping a little bit because it's running out of time. But so before finishing, yeah.
Your pseudonym compared to like incognito mode in the browser?
So incognito mode is giving. So there are several different research to actually looking into what exactly the incognito mode does. One thing is they are kind of stripping the cookie after a while. So at the application layer protection mechanism, and then it's a kind of separating into two different types of mode. So one mode is kind of private and the public. So we can say that this is one difference is we are building it in a cross-layer manner, and the other is we have more finer-grained control, not just the two modes, but you can have whatever you want. Yeah. So yeah, before finishing up, I want to kind of introduce a little bit of other work. So most of the work are still some systems research, but with connection to other fields like ubiquitous computing or applied machine learning. So I've worked on voice and the computer vision interactions, especially in the context of the mobile devices. So Analyfy was, we are trying to enable the spoken natural language interface for any of third-party applications. I was building in the Windows Phone, actually, and Visual Studio extension. And then I've been working on how can we efficiently run the neural network in a context of you have the mobile device and the cloud, and what kind of schedule we need to have for getting more efficiency. So I can talk anything about that in the offline or in one-on-one meeting later. So looking forward, I plan to continue the research in systems and security, also in connection with any other collaboration with other researchers. So one example, I will briefly talk about probably for the second and third one. So many researchers have been looking into the neural net in terms of how can we better accuracy? How can you get better accuracy? Or how can we have a faster training, because training takes too long. But in the real application context, there will be many requests. Many applications will use some sort of neural net classification. Then I could imagine that there will be many concurrent requests coming to the service side. Like there will be many users, there will be many applications. So what kind of architecture, system design we need to serve those requests more efficiently would be an interesting direction for me. And the last one, as combining from the system side and computer vision side and the privacy issues I've worked on. So it's pretty obvious, like if everyone is using some sort of computer vision application, and is it okay to send the data to the cloud and let them process it? Because it will definitely invade your privacy. So what kind of architecture to protect in those scenarios as one of the other direction I'm looking into. So today, I presented how we can give more controls to the users in the untrusted and unreliable environment. So as examples, I talked about a file sync service with untrusted storage and the pseudonym abstraction for the privacy control. And thank you very much, and I'll be happy to take any remaining questions.